introduction. Hi, I am Doganay Sirintuna. I'm a PhD student from Human Robot Interface and Physical Interaction Lab of Italian Institute of Technology. Today, I will present our study named as an object deformation agnostic framework for human-robot collaborative transportation. Transportation of objects is a commonly performed task in today's manufacturing environments such as factories and warehouses. For this challenging operation, human-robot teams can be employed in order to reduce the ergonomic discomfort of workers. In the literature, haptic-based controllers are utilized for co-transportation of rigid objects. However, when the object is deformable, then these conventional techniques may fall short since the object being carried may not transmit the range information. So in order to handle deformable objects, we need controllers that exploit different sources of information. For instance, in a recent article for the co-transportation of a cloth type object, a visual feedback and haptic feedback are merged. In another study, EMG signals are utilized for collaborative one-dimensional lifting tasks. Considering the previous studies, our main goal is to co-carry objects regardless of their deformation characteristics. In order to solve this issue, we present our framework that merges haptic information with the human kinematic information. Here you can see the videos that we are using our framework to co-transport different type of objects. In the leftmost video, you can see a co-transportation of an unstretched rope. In the middle, you can see co-transportation of a partial deformable bag. And on the right, we are co-transporting an aluminum rod. So in our experiments, we used the Kairos robotic platform. Our robotic platform consists of an omnidirectional mobile base and a high payload robotic arm. We attached a robotic soft hand at the end effector to grasp the object being carried, and we used Xsense mocap system to track the human movements. Here you can see our control architecture. Mainly, our control architecture consists of two main modules, the adaptive collaborative interface and whole body controller. In the adaptive collaborative interface, we are merging the admittance velocity, the haptic information transmitted through the object, and the human hand velocity to generate motion references for our whole body controller. And in our whole body controller, we are calculating the desired joint velocities for our robot. So here you can see how our adaptive collaborative interface handles the object having different deformability characteristics. This unit merges the haptic and human movement information based on an adaptive index alpha. In the second equation, you can see the calculation of this adaptive index. This index allows us to understand the deformability of the object on the fly. And for instance, if the object is highly deformable and does not transmit any range information, then the admittance velocity will be close to 0. And in that case, we can say that our alpha value will be around 1. On the other hand, if the object is non-deformable and transmits the range information without any loss, we can say that the admittance velocity and human hand velocity will be close to each other due to the rigid connections. And in this case, our alpha value will be 0. And if the objects having different varying characteristics in terms of deformability, then our adaptive index value will be between 0 and 1. Lastly, this unit calculates the desired pose and desired twists and sends them to our whole body controller. Here you can see our whole body closed-loop inverse kinematics controller, and it is based on a solution of a hierarchical quadratic program that composed of two tasks. The first task, the prior task, guarantees the tracking of desired end effector motion. On the other hand, the secondary task keeps the arm close to the desired joint configuration. In order to understand better how our controller works, we can compare our controller with the baseline controllers, namely admittance controller and teleoperation in the extremities of object deformability range. We consider these extremities as purely rigid, that transmits the range information without any loss, and highly deformable that does not transmit any range information. In addition, what we mean by like teleoperation like frameworks are the controllers that mirrors the human hand information to perform collaborative transportation tasks. Here, in this experiment, we used an aluminum rod for our purely rigid object. And when we look at the graph, you can see that the first row shows the end effector velocity of the robot, the second row shows the admittance velocity, and the third row shows the human hand velocity. And when we look at the data, we can see that teleoperation frameworks fail due to the rigid connections. However, when we use admittance controller, we can say that the co-transportation is successfully performed. When we employed our controller, we can say that the first thing we should say, the alpha value, our adaptive index, is around 0 all the time, as we expected. And with our controller, we can successfully co-transport the object in all 3 dimensions. For highly deformable objects, we use an unstretched rope, as you previously saw in this videos. And due to the lack of haptic information, the admittance control failed in this case. However, when we use teleoperation, like frameworks, we can say that we can co-transport the object being carried in all 3 dimensions. And here, when we employed our controller, the alpha value is always around 1, as we expected, and our controller acts like a teleoperation-like framework, and it caused us, we can successfully co-transport the object. And when we look at these 2 experiments, we can say that our controller can handle these 2 extremities. However, admittance or teleoperation-like frameworks fail in one of these conditions. In order to verify the effectiveness of our method, we conduct a user study. And in this user study, we compared the performance of our controller with the admittance controller during a co-carrying of a partial deformable object along a desired path. We didn't use teleoperation-like frameworks in this user study because when the partial deformable back is stretched during the co-transportation, then it acts like a purely rigid object, and this is why we cannot move we cannot continue the co-transportation. And in this user study, 12 subjects is participated, and each of the participants performed 10 trials. Here you can see an example experiment results. When we divided our experiment into 5 sub-tasks, lowering and lifting, pulling, moving sideways to the right, pushing, and moving sideways to the left. Here you can see that our alpha value is adaptively changing during the task according to deformability of the object. In the first task, in the first subtask, in lowering and lifting, we can see that our alpha value is around 1. However, when the object is pulled, it acts like a rigid object, and this is why our alpha values is around 0. And here you can see that in this graph, the measured end effector forces for average of all participants. And in the second subtask, there is no statistical significance between admittance controller and our controller, and it shows that our controller acts like an admittance controller in this case, when the object is purely stretched. In order to quantitative evaluation metrics, we use 3 metrics. The first one is the completion time, and the second is the alignment metric, which is formulated to evaluate how accurately the robot follows the human partner during co-transportation. And lastly, we use effort metric, which is inferred through the measured muscle activities of the selected muscle groups. When for the alignment metric, the lower values shows better results. When we look at the graph, we can say that with our controller, the participants perform the task faster, with less effort and with better accuracy. On the other hand, our participants filled out a questionnaire that composed of two parts. The first one is the custom questionnaire. And in our custom questionnaire, our questions are related to safety, usability, and performance of our framework. And apart from the questions related to safety 1 and 5, in all of the other categories, our framework has better superior scores with respect to the admittance controller. On the other hand, in the second part, the participants filled out a NASA TLX questionnaire, and in NASA TLX questionnaire, in all categories, our controller has better results with respect to the admittance controller. All in all, when we look at the results, we can say that our controller is more successful than the admittance controller during handling of deformable objects. So as the framework I present so far, we can only translate the objects being carried in 3D dimensions. However, when the question is, what if we want to rotate the objects during collaboration? So in the literature, this problem is known as rotation translation ambiguity, and there are lots of articles about that. The first one of the first articles that focused on this topic uses virtual non-holonomic constraints. And in this article, the movement of the object is constrained as if it were being carried on a wheel attached to the object. And in other articles, on the other hand, the current movement intention of the human operator is understood first, and the motion mode is switched between rotation and translation. So all these articles are validated with rigid objects, and they can handle rigid objects. However, when the object is deformable, then we need another source of information to handle these rigid deformable objects. Sorry, and maybe we can use voice commands to handle this kind of situation. However, these voice commands are not desirable for industrial environments. So in order to solve this issue, we detect the intention of human to rotate the object by using human torso and hand movements. So this is the framework I presented previously. Now we add these two additional subunits, object translation unit and object rotation unit. And in object translation unit, we are calculating the translational velocities. And in object rotation unit, we are using a novel algorithm to detect the intention of the rotation of the human. And we are calculating the rotational twists and sends them to the reference generator. And the reference generator merges these two informations. Here you can see the details of these units. The first one actually is the same unit that I presented previously. It calculates the translational velocity based on this adaptive index alpha. And in the second one, we are using a novel algorithm based on human torso and hand movements. To initiate the rotational movement, the human operators should rotate their torso to the desired angle. And by looking the human torso and hand movements, we are able to detect this rotation intention. The primary source of information of our algorithm is the relative yaw angle between our human torso and our hand. But human hands can translate even though we are can rotate even though we are just translating, and it can create a relative yaw angle between human torso and hand. This is why we are monitoring the human torso and hand individually to understand if the torso is rotating or hand is rotating. And based on this understanding, when we detect the rotation intention of human, we are calculating the rotational twist, and robot comes forward to the human. And in reference generator, based on this rotation intention, we are merging the outputs of these two units, and we are calculating the desired twist and desired pose. And we are sending them to our whole body controller. So you can show the video. Here we are using a mannequin on top of a sheet to show that we can handle objects, complex deformable objects. Here, the human operator starts to rotate his torso. This is me. And now, when the rotation intention is detected, the robot starts to come forward to the human. And when the rotation part is finished, we can continue to translate the object. So with the framework I presented so far, we can handle objects having different deformability, but there are still challenges to make the framework more generalizable. The first one is the co-transportation of heavy and bulky objects, when it's impossible to manipulate with one single robot partner due to the object size and load. The second one is the co-transportation of ungraspable objects. At this point, we are inspired of these deformable forklift moving straps that are used for human-human co-transportation of the objects in industry and in daily life. And we improved our framework to adapt it to scenarios where human multi-robot systems are needed to co-transport the object irrespective of their deformation characteristics. And with this new framework, we can handle any number of robotic partners without relying their particular structure of the robots. Here you can see an example video. Now, in this case, we are using an admittance controller. You can see our deformable straps here. We are carrying a 12-kilogram box. And due to the deformability of the straps, there is a misalignment between human and robot, and this is why we cannot co-transport the object. We failed to co-transport this object. Now we are using our controller and with these deformable straps. And in this case, there is no communication between robots. And we are using the haptic information and human motion information, as I explained earlier. So with our interface, we can handle these deformable straps. This is why we can co-transport these big and bulky boxes in all 3 dimensions. And actually, the woman carries the boxes with us here today. And thank you for your attention.
Questions?
Hi. Thanks for the presentation.
Thank you.
So maybe regarding the alpha that you use,
yes.
So how this can be compared to an admittance controller, in fact? Because let's say that you have an object that is highly deformable.
Yes.
So if you have an admittance on this, then, I mean, if it is not stretched,
yes,
then the admittance controller would just command the human velocity.
Yes.
Right?
Yes.
And then when you extend it,
yes,
then it will start, yes, when you stress it,
yes,
then it will start listening as well the human force.
Yes.
So this is what admittance is doing naturally, essentially,
yes,
right?
Yes.
So why do you need alpha then? Maybe you have said it, but just you can highlight it a bit more.
Of course. Can you go to the proposed framework? No, not this one. Slide number 5.
Yes.
Yes. So thank you for your question. So when the object does not transmit any range information, then basically this alpha goes to 1. And here you can see in the equation 1, we are using just the human hand velocity in that case. So, but if the object is transmitting this range information, then the alpha goes to 0, and we are not listening this human hand information. So this is thanks to this adaptive feature, we can co-transport rigid objects and deformable objects. But actually, you are right in your question, is that when the object is purely rigid, basically our controller acts like an admittance controller. But if the object is highly deformable, it just mirrors the human hand movements. But there are some types of objects that can act between these purely rigid and highly deformable. In that case, we are merging this human hand information and admittance velocity based on this adaptive index alpha.
Okay. And to follow up, I'm quite happy that I see that people watching the the rotation translation problem. Just a comment. I have a recent one in RAL that we used as well, motion from the tasks to address this problem. Yeah, just a comment.
Thank you. Thank you very much. I will read it for sure.
It's from 2020, from ICRA in China. The one.
Okay. Thank you.
I have a question linked to this one. May I go ahead?
Yes, go ahead.
Okay, so thank you for your presentation. So indeed, the fact that alpha is a continuous indicator is good for stability, but does it really make sense to have a value of alpha that is in between 0 and 1, in your opinion?
Actually, thank you for your great question. We wanted to normalize this deformability between 0 and 1, and based on this normalization, we can see that we can use this human hand information and admittance velocity between these normalization, actually. But maybe we don't need this kind of normalization, and we can find a way to combine these two information as well.
Okay, and do you have encountered objects which have a deformation pattern so that they need like a bit of admittance and a bit of human motion control at the same time, like you have alpha equals 0.5 or I don't know, something like this?
Actually, in our experiments, we use this kind of object, a partial deformable object, and in this partial deformable bag, these alpha values are moving between 0 and 1. Actually, we can go to slides, maybe experiments slide. For instance, in the moving sideways to the right or moving sideways to the left, you can see that alpha values are between 0 and 1. And in this case, we are actually merging the human hand information according to this alpha. And it helps to follow the robot to human partner accurately.
Okay, thank you. Thank you for your answer.
Thank you. Thank you for your question.
Hi, thank you for the great talk. I'm not super well versed on human robot controllers, but do you think that the questionnaire you performed helped you with finding future directions, or was it more to validate the controller itself?
Can you repeat your question?
Sorry, the questionnaire you performed with the number of questions about performance of the controller, was that more to validate your approach or to inform future research directions of maybe where this controller could have been improved?
For validating our approach, and we just want to validate if our controller can be used this kind of information, because we are combining the hand information, and with the new users, unexperienced users, sometimes teleoperation frameworks can be dangerous. When you move your hand very fast, the robot will follow your hand. And in this questionnaire, we wanted to see that if, in terms of also safety, it can be usable, or performance or usability, and this is why we put a questionnaire.
Can I one quick follow-up? So do you think that it captured things that were hard to capture with like just the metrics that people use for these?
Sorry.
Do you think that the questionnaire captured things about the usability of the system that were hard to capture with the metrics that you presented?
What metrics? Sorry.
You presented metrics like how much energy they used and stuff.
I see.
Do you think that it captured things that were hard to sort of write down by a number?
I get your question, and
Yeah.
thank you for your question. I think, yeah, we wanted to see a subjective evaluation of their feelings in the experiment. I think it can be related to the effort metrics we are using.
Thank you.
Thank you.
Okay. Is there any way to get the human information? Because for me, motion capture is still in the lab. Can we move the system or your method to outside the lab?
Can you repeat your question? Sorry.
Is there any way to get the human information? Because for me, the motion capture system is still in the lab. So how can we move your method to the outside the lab?
I see. We were considering to use actually put a camera to track the human movement on top of the robot, but depending on the object we are carrying, there might be some occlusions. This is why we used Xsense system, and Xsense system can give us a better smooth trajectory for human hand velocity without any jumps. For instance, if you use a camera-based system. But I get your point that maybe if we want to generalize this work to industrial scenarios, we probably need a better human tracking system.
How about detect the object shape? Maybe you can detect the object shape to estimate the motion.
Yeah, we can do that, and from that object shape, we can understand how is human moving. But in this work, we focused on to detect human information, but also we can use the object shape to understand how human works, how human moves.
Okay, thank you.
Thank you.
Thank you.
Thank you.
Do you think that preserving the applying shape control problem to this problem as initial shape preservation is equivalent to what you are trying to solve?
Actually, for instance, in the unstretched rope case, we are basically considering the first shape of the unstretched rope. If we don't have any draft coming from human hand velocity or etc. But we may need also some kind of haptic information during this collaboration. This is why we just